is to contain untrusted code, right? And we said there are two broad approaches. One way is to look at system calls that this untrusted code makes, and then enforce policies on how this, what system calls you can enforce, this code can use, and what are the arguments and so on. Okay. The second, and that approach is called external reference monitoring, because by and large you run your checker in a different address space from the check process, right? So the picture we drew for ptrace is an example, right? So you have the checker running in a separate process, and the check process or the monitored process has its own address space. Okay, and we talked about eBPF, which allows you to install checking code in the kernel, right? And once again, the checking code, because it runs inside the kernel, it's running in a different address space from the process that's being monitored. Okay. So a second approach is to say, I want to put the checking code right inside the process that I want to check. Okay, and that is called inline reference monitoring, because the reference monitor is actually deciding the same piece of code. Okay, so the checks are inline. Okay, the security checks are inline with the accesses. So running the putting the reference monitor inside the checked code has some advantages. So, for instance, you could express policies that are not expressible in the other frameworks. So, for instance, you could say the policy I want to enforce is that variable x is always greater than variable y. Right? So this is not something that you can enforce by looking at system calls, right? Because x and y are being updated through memory operations, and they involve no system calls. So you can't possibly say, I'll check this when a system call is made, and it's not meaningful. And secondly, because you are working within the check process, you basically have, you can be operating at a higher level of abstraction, because you can look at its data, you can look at its the functions that it calls and whatnot, and therefore it can be easier to express and enforce certain types of policies than what you can do at the system call layer. Okay, and of course it can be very efficient, because there's no context switch. Everything is the same piece of code. Okay. Now, of course, all of that doesn't come for free. The main problem is, well, if you're talking about malicious code, is it possible that this code will try to defeat the checks? So this is the problem that we need to think about. Okay. So this is the problem of having the reference monitor, which is performing the checks, sharing the same address space, right? Therefore, you can so think about a simple problem like the reference monitor needs to have some state, right? It's not a stateless checker; it has some state. Okay. Now, if this state is going to be accessible to the checked code, and if the checked code is malicious, then it can modify the state and then thereby defeat the checker, right? So this is why one has to be very careful in designing these inline reference monitoring techniques, and so that's sort of what we are going to talk about in the next today and in our next lecture. Okay, and this problem attracted attention about again in the mid 90s in the context of an approach called software-based fault isolation. Okay? And that project was tens of years ahead of its time, and so we are still basing many of the modern you know, security checking techniques on some of the ideas that were developed in the context of this project. Okay, so what I'm going to talk about going forward is going to be mainly about untrusted or potentially malicious code, but sometimes we apply this kind of inline checks for doing a lot of vulnerability mitigation techniques, right? So, for instance, you think about canaries, right? So you have you write a canary, you check the canary before the doing a return, right? So that's an example of an inline reference monitor, right? So what is the state that could be corrupted, right? So for instance, the canary value, if the process is malicious, the process would simply overwrite the canary value with something that is easily guessable, right? So for instance, if it puts a 0 there, then a remote attacker can easily circumvent the canary because the attacker knows what the canary value is, right? So so clearly, this kind of inline reference monitoring is not good if you are talking about, or rather, propolis and stack canary checks are not robust, inline reference monitors if you consider a threat model of, untrusted code. But if you think you're just dealing with a vulnerable code that doesn't have any malicious code already running there, then it seems like a reasonable thing to do because you think, okay, because it's not already malicious, it's not going to go on and try to subvert the checker. Okay, so as a result, a lot of what I'm talking about is related, but issues are not as serious for when you think about vulnerability mitigation. So another way of saying it is that pretty much all of the vulnerability mitigation techniques use inline reference monitoring, but they are not secure in the sense that we are going to talk about, okay, because the threat model is that of a weak attacker. The attacker doesn't have any ability to run code yet, and therefore the attacker's capabilities are limited, and in those circumstances the checker doesn't have to be that robust. So let's talk about software fault isolation. So what is software fault isolation? The idea is, so the whole concept was not so much based on security, but performance. Okay. So, but before understanding what the project was about, let's define what fault isolation means. Fault isolation means, you just look at the English words, right? So, if a fault happens, it's somehow isolated. So, the reason why we have why we separate different processes into their own address spaces is actually for fault isolation, right? So if there is some process on your system that crashes, that doesn't affect any other process. Right? So long ago, when people used to use Windows 95, right, they didn't know that this was a feature, right? So this wasn't possible. So in Windows 95 and earlier systems where there wasn't address space separation, processes could accidentally or intentionally interfere with each other. They could in fact even corrupt the kernel, right? So good operating system design says, well, you should if you want to build a reliable operating system and a reliable set of applications on top of the operating system, then you need to have these idea of fault isolation and implement it, right? Make sure that faults, the effect of the faults are localized. Yes, something is going to crash, but let's keep that to be a small component rather than the entire operating system. Okay. So if you this is good, either because there are bugs in any piece of code, and sort of expecting a small bug in one component to bring down the whole system, that's not a good way to build it. Or you could think about it in terms of malicious or untrusted code, and then you could say, well, I don't want to make just because I run one piece of untrusted code, I don't want my entire system to be compromised. Okay. So, but the basis of all of this fault isolation, which obviously exists in Unix since its very early days, was based on address space separation between different processes and between the process and between the user space and the kernel, right? But that was always based on having some level of hardware support for address space separation, right? So the idea was that somehow the hardware needed to mediate the memory accesses and needs to check that one process is not able to access memory space that is set aside for another process or the kernel, right? So people, the reason why this software fault isolation came up was that people thought, well, this kind of hardware-based thing is expensive. Again, the context switch is the problem, right? So, so what if I can, avoid this hardware-based approach and build isolation right within the software, where you have two modules that are running within the same address space, right? But one module doesn't trust the other, and there are checks to make sure that one module, the way it accesses another module, those accesses are checked and so on, right? So how can we do this without really having to run them in two separate address spaces, right? And again, the real issue is, will this give us performance? And that was the idea, but of course, performance will be useless if you don't have security. Okay. So what they tried to do was, okay, there is this whole address space. Think of this as a virtual address space of a process, and within that process, you want to run some untrusted code, and you want to limit, what can happen when this untrusted code fails. Okay. So for concreteness, let's not think about failure. Let's think about attacks. Okay. So we want to make sure that this piece of code, right? Which there are two parts here. We think of one of these as code and the other as data. Right. So this is an untrusted module sitting in the middle of this process address space, and you want to make sure that this untrusted module can only run its own code, and it can only access its own memory, right? So the rest of the process address space, you can think of it as maybe trusted, and this is untrusted, and untrusted accesses need to be limited. Okay. So how can we do this? So so the idea was, okay, so let's think of a design, and the design they came up with was to say, okay, so let's just say that this code segment corresponds to certain small part of the virtual address space, and you can say, okay, the leading 8 bits have to be 76, right? So that means if you fix the leading 8 bits, that means you are basically giving it 1 by 256 of the total address space, right? Because you fix the first 8 bits, so that means you're letting it access any address with that particular byte as the leading byte of the address. Okay. Same way you can do that for the data, and this way you can limit the access. Okay. So this is sort of what you want to do. You want to limit it to this small region of memory. Now the question is, how exactly do you do it? Okay. So how can you ensure that this, let's take a simple problem. Okay, this piece of code, when it runs, all the data accesses it makes should go to only this data segment, which let's say has the leading byte of 76. Okay, so now how can you make sure of that? Anybody wants to guess? It's the most obvious thing you could do. Yeah.
Just export this and make an export.
So rather, you're talking about how you do it, but the point is, before every memory access, you check whether the leading 8 bits are 76, right? So this is what you do. The main thing is, of course, you need to make sure that every memory access it makes, right, needs to be checked. Okay. So they call this as segment matching, which is basically checking whether the leading bits match a particular value. So let's look at how this checking code might work. So before the memory access, right? So there is a target address that you compute. Okay, so this piece of code is trying to access a target address. So you move the target address into your register. You shift it to the right so that you only retain the leading byte or leading some number of bits, and then you check that leading bits against what is the correct value, which is stored in a segment register. And if it's not correct, then you're going to say sorry, okay, and abort the program. So again, there's nothing difficult to understand here, but there is one concept that you need to sort of think about why it's there. So it says that the target address needs to be moved into a dedicated register. Okay? And it says that the segment register should be a dedicated register. Okay? So what dedicated register means is that the untrusted code is not allowed to use that register for any other purpose. Right? These registers are set aside for use in these security checks, and they are not going to be used for any other purpose. Okay? So why is it necessary to set aside these as dedicated registers? Anybody wants to take a guess? Yeah.
So the attacker doesn't have access to the registers?
So, in effect, yes. The interesting thing is, what kind of attack are we talking about? Right? So why is this? Because so the design was simple, right? So the design was simple in the sense that all you're going to check is whether the leading bits are within your address space, right? And you're going to do this, although I talked about data accesses, you obviously have to do that also for code access, right? Because you want to make sure that it doesn't jump out of its own code, right? But both checks simply involve verifying that you are within your region, right? But if you jump to arbitrary places within your code, right, then that's not checked. So what if the untrusted code simply jumps, directly here. So here is the store instruction that uses the dedicated register to do the store, right? If you jump to this location, right, then it looks like you have bypassed all the check. Okay? But if you make sure that it is a dedicated register, then what you will be able to prove is that the dedicated register always has a valid value. Okay? So if the dedicated register always has a valid value, even if the attacker tries to jump and do all these things, that's not going to help the attacker you know, evade any kind of check. And the same reason, the segment register that stores what is the leading bits also has to be dedicated, because once again, if the attacker has control, then they can jump from some piece of code where they set that segment register to something, and then they can jump over here and suddenly, some piece of some check to be separated. So what they wanted to do was they wanted to, defeat these attacks that involve this kind of, circumvention of checks by simply making sure that these registers are never under the control of the attacker, and therefore they will always have a valid value, and so the attacker cannot escape. So this particular implementation is not very efficient. You can imagine that before each memory access, I have to do this 5 checks, and I have to set aside so many dedicated registers. In fact, there are 5 dedicated registers required, because some of these registers, like segment registers and dedicated registers, have to be separate for code and data. So instead of the shift register could possibly be shared, but the segment register and the dedicated register have to be different for code and data. So you end up having to have 5 registers. And if you think about processors in the 90s and 2000s, mainly people are, especially 2000s, mainly people are using 32-bit x86, which had 4 registers, right? So very small number of registers. And so this type of technique was not very effective. Even on RISC processors that had more registers, still the number was not that much. So so the paper also introduced a somewhat better approach, which they call as address sandboxing, and the word sandboxing is in wide use today. We use it to say, okay, we run this code inside a sandbox, but the origin of that term is from this paper. And what they had a particular meaning for sandboxing, and that was that rather than doing a check, right? So they basically take the target address, they shift it, and then perform a check whether the leading bits are allowed. Instead, in sandboxing, all they did was they would just force those bits to have a certain value, and then you don't check. You just force the value, and then you keep going on. And this is what they call as sandboxing. So even if the code tries to get out of its region, it's not going to succeed, because you're going to force it to be in its region. And this approach